Hello and welcome back. My name is Corey, and this is the series where we work on a programming language from scratch, 100% live coding. And if you were here for the last episode, I will go ahead and apologize now for the quality of the sound. I don't know what happened, but it was bad, and I know it was bad, and I've tried to fix it here. We'll see if this fixes it or if anything else is going to mess with my sound settings. But we are working on Tang, a template language, and when we say we're doing everything from scratch, that means if we don't write it, it doesn't exist. And I had planned on working on for loops, but I've been thinking about it, and I want to get strings into this language. And we're just going to jump in. We're going to do it. So, as usual, if we look here, let's see. The very last thing we did, as you can see, is, there it is, episode 28. That was the very last commit. And as I've been saying, nothing up my sleeves. This is just picking up from there. Get status, there's no code changes there. We're going to add strings. Oh boy. Oh, I actually should have brought up my references that I was going to use. I will do that little by little as we are getting through all of this. I know specifically what strings, what I'm worried about and what I know I can't do off the top of my head. So anyway, all right. Let's see. We want to have a computed. Yeah, we want to have a computed type that is a string, but we also need a string literal in our AST. Where do we want to start? So it's basically we're adding two things to the make file. And do I even want to do that yet? Yes, we will. We will start with the make file. There's not a good or a bad place to start. It's going to require this. So where is this going to go? After the AST node integer? Sure, we'll put it there. And it will be AST node string. All right, and that's going to define a string literal. And then we also need a computed expression string. And I guess that can go after, well, error probably should have gone somewhere else. But you know what, we'll just start from there. Yank, put it there, computed expression string. All right, now we need to include, we'll just put it here. On 86 and 87, what are we going to do? We're going to substitute integer and put string there in its place. That's fine. And now we also need this for the computed expressions. Computed expression, well, we'll integer, sure. Just for the same thing. And we'll do the exact same substitution. Integer. Oh, because I need to change the line numbers. That's why. So now this is 141 and 142. Simple enough. Okay, so now we've told our program that we want it to look for these things. Let's copy them. So we're going to copy the source for AST node, and which one should we use? We'll start off with integer. Why not? Integer, and we'll call this source AST node string.cpp, and we will do the same thing for the include AST node integer for include AST node string.hpp. And now we need to do the same thing with our, we'll do source, computed expression integer, but we're going to copy that to source computed expression string.cpp and copy the include for AST node, not AST, computed expression integer include computed expression string.hpp. Do I have that right? Looks like it. All right, now we know that we need to start editing these. So always do include first, just for my own mental, keeping everything straight. And then source computed expression string. I should have done the ASTs first. You know what? I don't care. It doesn't matter. All right, computed expression.hpp. Let's %s, and we will say capital integer. We'll change to capital string globally, and we will do the same thing. %s title case integer will change to title case string globally, and we'll go to the next one. Exact same things. Okay, and I'm going to go ahead and open up the ASTs. The include AST node string is what I'm looking for. And the edit for the that's the include. The source, src, there we go. src AST node string. Okay, and now we just need to do that one was the all caps, this one's the title case, and this one is going to be there's the all caps, and now for the title case. All right. Now we're back to the computed expression. I just went to the first, right? We've got all of these buffers, and I just went back to the first one. BF, if you're curious as to what I was using. And before I get too far into this, turn my phone on silent. That way it doesn't start ringing very loudly. All right, so we've got represents a string that is the result of a computation. That is perfectly fine. Construct a string result. Sure, why not? And this will be val. I'll stick with val. This should be the string value. And the only thing is we don't want an int64. We want a standard string. And so for up here, we're going to need to pound include string. All right. Dump is, I guess it was already included by computed expression. Never mind. Is equal. We're going to add an is equal const string. There we go. And that's the only one we're going to do. We might do, no, that's all we're going to do. We'll leave the add, but there's not going to be a way to subtract, multiply, divide, modulo. Maybe in your in your language you'll want to do that. Should we have less than or equal to? We can leave those in here. Yes. And what about the not? Well, we can leave that. Integer, no. Float, no. But we'll leave the Boolean. And we can actually use the Boolean to give us the not. All right. We don't need the friend class for the float. This will be the string value, and this is the string. Okay. Simple enough. So we kept is equal for a string, which doesn't exist yet. We're going to be adding that. And we need to add the add not less than equal in Boolean. All right, so up at the top, computed expression string, we need this to be a string val. Okay, the constructor is now good. The dump is going to be just this val. Simple enough. To make a copy, we make a computed expression string with the val. That's also easy. Is equal. We said we were going to do a string. Is that right? BP. Constant string ampersand. Yep. All right. And just say, is it equal? And so that means we don't need that one. For the add, all right, we're going to say if the one on the right-hand side is a string, then we know how to handle it. And all that we're going to do is, okay, so we're converting it to a string, and we're going to make a string where this val plus, you know what? That is perfectly fine because a string can add to a string. And otherwise, we don't know how to add them. So, yeah, that's simple enough. We don't need, I'm just getting some space here. We don't need to know how to subtract, multiply, so I can get rid of those. Divide, modulo, don't need those. Negative, don't need those, but will that work? Well, I mean, just the calling for the this arrow val. That might work. For the less than, that should work. Equal, we should be able to keep that because we're just treating it, yeah, is a string equal to or is it less than? That should be just fine. We don't need to convert it to an integer or a float. And the Boolean, I don't know. I've worked with too many other languages. I don't know off the top of my head if I can convert from a string directly to a Boolean. If not, I'll just check the length of the string. But I don't need computed expression float, and I don't need computed... I do need error and Boolean and string. Okay. This seems to be going rather okay so far. Now we've got the string class, an AST node that represents a string literal. Strings are, nope, I don't need any of that. The constructor, and this is no longer going to be called number. It is going to be text. The string to represent, sure. I'm hitting the wrong buttons here. That's all right. Okay. That should be fine. I'm just going to have to remember. Before, I was just passing an int64 because it was an integer. No need to do the const reference, but in this case we are. To dump it, that's fine. To compile it, okay. And then this needs to be the string value being stored. And the only other thing that I didn't do is pound include string, but it should already be there because it's in AST node. Yes. Okay. And now for the AST node string class, string now we need this to be a const string ampersand text location text and am I using val? You know, I use val on the others. I'll stick with val here. So that should be text and then val. I think so. And now the string. So I want to have a double quote. I don't need that, but I do need to end, whoops, with a double quote. Okay. That should be fine. And now how do we... The opcode doesn't exist. I know it doesn't exist. But we will, I'll leave that there. So string, and this isn't going to work, but we can do the this val dot length. I think it's length. And then we're going to need to do write loop to add characters. And this is not the length really. We're going to need to pound include, I think, CMath. You know, we'll cover it. We'll get there. I also know I need to edit the opcode. So that should be include opcode. And we're going to do, if we've got a null value integer float boolean, we're going to add string, and it is going to pop the length, pop chars, push, not pop. It's going to get the len and char string. Oops, there we go. And then it's going to push that string. And I'll just say get, because they're going to be in the opcodes. It's going to be embedded in the opcodes. And you say, how do we do that, Corey? Well, we're about to find out. So now, first we're going to, it's probably going to complain, but I'm going to say make test watch, and it should give me a few errors, I'm hoping. Okay. So, oh, I don't have the is equal for a string, and that is in the computed expression. So do we need to add that to the garbage collected as well? Probably. So that's going to be the, let's start off with the include for the garbage collected. Garbage collected, operator equal. No, that's copy assignment, move assignment, destructor. Yeah, it's all of these. We got an error. You know what? We did this here. Int, double, bool. And now string. And now we're going to edit the source for garbage collected. And we're going to need to add that operator double equal for a string. Okay. And the HPP, it still doesn't like that because we haven't gotten to that yet. So we need to edit the include for computed expression.hpp, and the is equal, we'll steal the Boolean one here and duplicate it, and now we will have an is equal const string. And now it's going to complain because there's not a default for that, but we're about to provide that default. So the source for computed expression, CPP, we've got the is equal for a Boolean, copy it and provide it for a string. And now, let's see, yeah, it doesn't like the not. That's okay. So let's go back to our computed expression string.cpp. That should be 2. Yep, it is. On line 38, we're there. And instead of not, .val, we'll do length because, there we go. And, oh, line 65. And it doesn't like this. We'll say dot length. Is that right? By the way, while I'm doing it, so if it has a length of 1, Boolean value will be true. If it has a length of 0, the Boolean value will be false. Yeah, that's good. Okay, so it's compiling, and it's not going to be working yet, but we're about to get there. And yeah, let's write a test just to show whatever. So we're going to be able to declare integer float add, wait. Did we have a declare for Booleans or did we not? That should have been a declare. Pardon me while I move this up. I'm going up now. Yeah, integer float Boolean, and it should not have been an expression. It should have been CL declare. And now we're going to have a declare as a string. And of course, the problem with this is I have to say hi, and it should be hi. An empty string should be an empty string. And we can even expect, is it NEQ or just NE? I think it's NE, not equal. That should not be equal to null pointer. Sure, why not? Okay, and probably it should be failing stuff now. Hopefully. Yeah, it's returning a null, and it's printing out a high. And that one, so yeah, and it does say 62 is failing. Oh, and it's an actual null. Interesting. All right, that's fine. Now, what we've got to do is we need to tell Flex how to recognize a string. That's the first problem, and it's bigger than you think. The second one is that we have to tell Bison what to do with it. And the third one is we have to figure out how to encode it, how to compile it, and then how to interpret it, to execute it. 4 problems we've got to solve in the next little bit. So, okay, let's go to Flex. And we'll start saying, what is the problem that we need to solve? Well, I'm just going to add a few lines here so that I can... this is not Flex code. This is just me being able to explain this to you. If I have a double quote, that's fine. But I should start recognizing things as a string. If I have the word if, I don't want it to say, hey, I found an if. Or if I have a do or something like that. I don't want it to be parsing any of these. Okay. And if I end a double quote, I want it to stop parsing that. If I have just what I just did, a slash, a backslash, I need to represent or recognize that as a something that's in the string that doesn't end until it has a single double quote. Or what if I have a slash n? That needs to be interpreted as a new line. So just recognizing a double quoted string is actually quite difficult. So that's why I was going to grab my notes. And do I even have this? Yeah. Okay. So what I'm going to do is, oops, undo all that. I'm going to add, I don't need a comma. So script and initial are kind of the first well, script I'm putting there because I know I'm going to need it. But initial is when you start parsing, it's in this mode or state. Well, they call them parsing modes. Hey, I've got it right there. And oh yeah. For it says it's useful for microparsers such as for comments or parsing C-style double-quoted strings. And if we go to this link, it's not there. Link rot has set in, and that link doesn't exist anymore. Neither does this one. Okay, I'm going to have to find a new reference for this. Nevertheless, we will press on. So what's going to happen is we need, a double quote string. That is a mode. It's like we're going to be in this initial thing, and when we see a double quote, we're going to switch to this other mode. And instead of parsing all of these rules, the if, else, do, while, or looking for all of those, it's now going to be looking for a completely different set. That's what we want. Okay. And in order to do this, I think we're going to need, right here, this says include any initialization code here. They have to be indented, otherwise Flex will try to interpret them as these rules here. So what are we going to do? We're going to have a, and we're going to call this the string buffer. And we're going to use that. And we're going to say this exists, holds the contents of a double quoted string as it is being parsed. And that should make sense. Now, okay, in our initial script right here, I'm going to start off, and I have to escape it, but have I seen, when I see a double quote, if that is the case, then that string buffer, I'm going to clear it, right? That means it's going to empty it out, and there's a function called push state. And it is, what is the name of the state? That's what I just provided up here at the top. Script is one potential thing. Double quoted string is another. So double quote string, not quoted, double quote string. And I need to return something. Do I? Pardon me as I think this through out loud. No, I don't have to. I think I can get away with not returning anything here. May get myself into trouble with that statement, but for now that's what I'm doing. And close it. Yes. So this is Okay. There we go. Now, I pushed this state onto a stack that Flex is keeping track of. Not me, Flex. And now we need to, okay, what do we need, when we go into this state, what will that look like? Well, down here all the way, I could just say at the bottom, and that's the state for initial. How do I know that? That was not, oh, that's why I hit Control F instead of, for forward instead of Control up. But if I go to this brace here and hit, oh, it doesn't match that because it's interpreting this. Never mind, never mind. Just, I know it is. Okay, so I need another one. And we're going to call this, nope, I'm pretty much going to be flying by the seat of my pants with this. Okay, well, we're going to call this double quote string, and all of our rules are now, it's going to be using this set of rules. So I saw a double quote and I switched to this and I cleared my buffer. So what happens if I find another double quote? And we're just going to do this one first. What should happen? Well, this is found the end of a double quote. Okay, so I need to pop the state, and now I would return a Tang parser make string, which we haven't put in the Bison parser, but that's fine. String, and I need to give it the string buffer and the location. All right, so right now we should recognize an empty string. That should probably be our first test. Do we recognize an empty string? It's going to complain because it says, hey, I don't know what make string is, but I'm going to go back to our tests. That's 10. And for a string, oh, it's number 2. Okay. So sorry, yes, I want this to be 1, this to be 2, this to be 1, that can be 2, and that can be 2. And in fact, let's leave that there because it should not equal a null either. And now we need to edit the Bison, and we're going to go forward. We're going to have right up here, we've got a token string identifier. Okay. Well, now we're going to have a token of a string, and it's just going to be called string. Sure, why not? All right, and what would we need to do? If we go down here, what would that look like? And the answer is it's an expression, right? So an expression can be an identifier, integer, a float, a Boolean, and now we will have a string, AST node, didn't mean to do all of that, string, where we pass in that string and the location. It's going to say I don't know what a string is, an AST node string is, because I did not do the pound include for it. AST node integer boolean string. See if we get some compile action here. Flex scanner is jammed. And notice it didn't fail on the first one. It just got stack is empty because we haven't written how to compile this. So yeah, that's fine. But the interesting one is this flex scanner is jammed. Why is it jammed? Because we haven't told it what to do if you find something inside the double quotes. Need to do that. All right, so let's go back to our flex scanner and let's do our yes, I'm double checking my notes of all the different things that we have to kind of think about. I want to kind of match the C style things that you can have in a string. I may not get all of them, but let's just start off. I know that there's one in which you can have an escaped octal number, and that starts with a slash, a backslash, but that's a special character, so I have to, it's a double backslash, but that represents a single slash, and a number 0 through 7, 1 to 3 times. Yeah. And I'm just going to say interpret an escaped octal number. How do we do this? So YYText, YYText is a C style string. We can do this. Okay. YYText, but 0 is the slash. So YYText is what it matched. So it's going to start off with a slash. So YYText sub 0 is the slash. I don't care about that. I want sub 1. And I know that it must exist because it matched this pattern. So minus, that should have been a minus. Evidently, Corey can't type. Where is the minus? There it is. Minus the character 0. And that will give me the value of it as a 0 through 7. Okay. Now, if YYText 2, why is this safe? Because YYText is a C-style string, which means it's null terminated. So if it's not a 0, then that means it is something valid and I can look at it. So I'm going to say result result is plus equal is that right? Well, I'll tell you what I was going to do. I was going to say YYText sub 2 minus the char 0, that's fine. Shifted left by 3. Why? Because that would shift left by 3. These are octal numbers, so that would be times 8. But if this is the second number, I think it should be result is equal to if it was 0, 0, 1, 1 would only have that. So I need to multiply. Okay. Yeah, I think this is wrong. This would be YY text. Sorry, I can do it that way. Plus result shifted left by 3. Or result shifted left by 3, and this can be a plus equals. I haven't done something like that in a while. In fact, I rarely get to, so I'm writing it. All right, so I know that YYText2 exists. Now I can almost do the same thing, but for 3. Yeah. And last but not least, yeah. Sorry, I know I keep arguing with myself. I just want to make sure that I'm doing this right. So the string buffer is now just going to get result added to it because it is an unsigned char, and this octal number will fit into it. Yep. Okay, that's an octal, an escaped octal number. And I'll have to double check to make sure that I did this correctly, but I think it is. All right, so what's another one that it could be? Since I looked for a slash and 0 to 7, yeah, because I did that, I now have to say, well, if I did a slash and any other numbers, 0 through 9, 1 or more times, that should be an error. And I'm going to say return a Tang parser make string. No, not a string. This is going to be a string error. And what should I... I'll just give the location. All right, so now we need to go back to bytes and just add this string error. And we should be able to do this as simply as I have this here. And instead of it, I don't even need a type associated with it, and it is a string error. And I'm going to say a malformed string. Sure. Okay. So I should be able to do an octal number, and anything else will be an error. Now, why does it work that 0 through 9 plus? Because order matters, right? So I declare the octal one first. So if it sees /3, it's going to optimistically be able to handle this. But, you know what? And I'll just add a comment here to say generate error. Bad escape sequence. Something like 48, right? Because 8s can't be in there. Or something like that. Too many characters. Okay. That's fine with me. And now let's do a few more. So what if I find a new line? Or, now the double slash is, it gets interpreted as an actual slash. So I see an actual \n. This matches either an explicit or escaped new line. Okay. And I don't think that C or C++ will do that unless you use the new, it was a raw string where it's an R double quote open parentheses or something like that. Yeah, okay. So all that I need to do for this is string buffer, add a new line. Okay. What if a T or tab? There we go. Put in a tab. What other characters are there that I want to... Let's see. All right, this is just so I can have some room. What if it's an R? That would be a carriage return. So I'm just passing things through. The bell character? Sure, why not? And you know what? I think... I don't remember why I had originally written down that I wanted to support these. I may have had something in mind. But this is the form feed, if memory serves. I don't have the vertical tab in here. But you know what? This is probably fine for now. Okay. Sure. Now, what about this? And this is a slash of anything else or a new line. Any other escaped character. That's pretty much what it is. And we'll just say YY text 1. So we're just adding that one character. All right. Okay. This will be an interesting rule. Now, the square bracket means a character class, and if it starts with a caret, that means not. So if it's not a backslash, a single backslash, or a new line, or a double quote, and I get one or more of those, then this is any other character in the string. And we're going to just say string buffer plus equals YY text. All right, and then last but not least, we will have the double slash, and I'm going to add this. Let's see, because we specified characters, we also need to specify what to do if we see only a single backslash at the end of the input. And that's what that would be. And the answer is we will return a we did this earlier. There. And that's okay. Now everything should compile. Flex didn't give me an error. I saw it scroll by. Still not gonna have everything because we haven't decided how to compile this. Yeah, insufficient stack depth. We haven't said how what it looks like to compile this information. But we do have Flex set up so that it should parse this stuff. Let's figure out how we're going to compile it. That's going to be in the AST node string.cpp. So buffer 4. So the opcode string. Well, let's before I do this, I want to do the source program dump bytecode and the source program execute. Okay, so the dump, we've got this here. We added, where did we add? Opcode is number 5. And then we'll come back to 13. We added the string after the Boolean. Okay. Going back to 13. After the Boolean. Oh, that was, I missed it somewhere. Found it. string. And we've got to check 1, and now that will tell us the auto size is equal to this bytecode of PC plus 1. Didn't mean to. Now the problem is bytes is going to be equal to, and here I've got to pull out my C++ ceiling, C-E-I-L. Yeah. Give me the actual. There. Yeah, in CMath. The ceiling of size divided by size of uint 64t. Why don't you just, Corey, you know what this should be. I know that. I mean, it's 8. The size of uint 64t is 8, but who cares? It's going to be optimized out, and it could have been a shift right by 3. I know that. But that is how many bytes it's going to take up. So if it's 0, it's going to be 0. If it's 1 byte, if the size is 1, then it's going to, the bytes is going to be 1. Up through byte. If it's 8 bytes, it's still fine to be 1. Yes. If it's 9, it will get 2. That's fine. So now the PC is going to be plus or equal to bytes plus 2. Why? 1 for the opcode string, 1 for the actual size stored as a number, and then 1 for all of the places that hold the string. We'll come back to this and get a way of pulling out those bytes. But for right now, that's fine. For right now, this should work. And opcode string, that should be all caps. Everything else should be fine. And now we're going to do the same thing after Boolean. In fact, there we go. Now we need execute program check. And it's still going to be the same thing, except we don't need to actually print out anything. And in fact, in the previous one, this is not right at all. This should have been that. Size bytes. Yeah, I like that better. All right. So what's it not liking? In the execute, seal is not declared, probably because did I not? On 101. Oh yeah, I found included CMath in this one. I must not have done it in the next one. All right, it's still not going to like it, but that's fine. Stack is empty, blah, blah, blah. I know that. It's somewhere around there. There we go. So the bytes is equal to that. The size is equal to that. So it went along just fine. If I just want it to get through, I could say stack.push back garbage collected make computed expression string. I should be able to do that. Oh, of course, need to pound include it. 129, okay. All right. It's not giving me errors, thankfully. I wonder, I think it's 9 is the test. Is that right? Nope, I'm wrong. Okay. What's test 10? If I, instead of just pass it an empty string here, if I say string of that, if it's going to pass the first test. It does. Okay, so this is going to be in my garbage collected.hpp b6. We've got a check for the const string. We're going to give another one for the const char star. Will that work? A reference to a pointer to a char? And this should be a I'm still not liking it. I'll have to come back to that at another time. I don't think that's going to fix it, but yeah, it's not liking line 62. Make this work. All right, so let's go back. And the big problem, we're down to the last two problems, believe it or not. We've got to figure out how to encode the string into the opcodes and then how to execute the string out of the opcodes. And yes, so let's look at the encoding first. Yeah, let's look at the encoding. So that is going to be in the AST node. So buffer 4. Write a loop to add characters. I'm going to need the pound math. C math. And actually, I think I'm going to need pound include is it here? I was looking this up earlier. I think I'm going to need that is not the right one. No, that's fine. I'll put this in the table in the browser with the other one. Mem copy, and that's in string.h. Is that C string or is it quite literally string.h? I'll leave it for this now. I'll test it. I don't remember. I used to know this stuff. I used to do this off the top of my head. Okay, so we need to I is less than length and plus plus I. That's fine. So we're going to iterate through. I don't think I want this. Temp. And what am I going to do? I am pack the characters into the bytecode. That's the goal. Pack the characters into the bytecode. So what I'm going to do is for each character, I want temp or equals. That should be a bitwise or. I'm going to double check that. I hope it's not. Just like, give me the C++ references. Come on. Just pulled up two things. Operator overloading, blah, blah, blah. What I wanted to know is if this is the logical or bitwise. And I'm not seeing it, but there we go. You know what? Is pipe equal bitwise or logical. I think it's logical. That's you know what? I'll write it the safe way, and then we will figure it out later. So temp is going to be equal to temp bitwise or, and for t as a I'm just gonna save that and make sure it compiles. Looks like it's going to. Yep, forget the fact that it failed. Okay, and now if it's done this 4 times, how do I know if it's done it 4 times? If I mod 4 is equal to 3, then add bytecode of temp, and temp is equal to 0. Reset it. Simple enough. And now once we're out of it, we'll say if this val.length mod 4, so if it has anything, so if it's equal to 4, it'll be it will have fit perfectly up here, and I don't need to do anything else. But if it's not, then it will have a mod 4 of 1, 2, or 3. If that's the case, then we'll catch that here, and we'll say pad the last byte. Not the last byte, but the last bytecode and push. No. Yeah. And add to program. Sure. How are we going to pad it? We're going to, because temp is already populated with the values. So imagine it had 1 value. And that means that the val length mod 4 is equal to 1. And I need to shift it over. Wait. I'm wrong. I should not be using 3. I should be using size of uint 64t. Now you say, Corey, why are you writing it like that? Why don't you just put an 8? Because that's how big it is. The reason is because in the future, I may find that 64t is too big. I may change that down to 32t. And I want to be able to find it. And yes, somebody says, well, it's still almost a magic number. Why aren't you using doing a type def on it so that you can call it your own name? And I may do that. I just haven't decided to do that yet. But I'm thinking about doing it anyway just because of the problem with floats. But for right now, so this should be size of uint 64t. So this is up to 8, right? So if it's 1, 2, 3, 4, 5, 6, or 7, I want it shifted over however many. So how many should that be? Temp is going to be shifted left by how many? Oh, that's going to be Can I do it this way? I think I can. We'll find out. Because the reason is that will give me the how many it's actually taking up. So I think I can do 8 times 8 minus I. Should never try to write clever code. But while it's compiling, let's see if we can figure it out. Oh, I'm in B4. B10. For the high, well, I'll do it for both of these. I want it to be cout p1 dot dump bytecode, and then we'll do the same thing with p2. And this will at least let us see the first one is failing because stack is empty. That's fine, but it's it's pushing on a boolean and a boolean. Corey messed up on something. On the dump, string, it should say string. Do this again. Say, Corey, this is taking a lot longer than I thought. Trust me, I've been dreading this. Why? Because it's going to get worse as we add in Unicode and stuff like that. For right now, I'm just trying to get it to do strings, period. Oh no, that wasn't doing it wrong. The first one is an empty string, 0 bytes. That's correct. The second one is this P2, and that's the one that's failing because it's failing on line 68. So the second 0 string, I was like, why does it not include? That's why I did a make clean and redid it, because Corey wasn't understanding what he was seeing. So it should be 2 bytes, and yeah. All right. So and a pop after that. Is that right? Why did it have 2 in a string? Oh, because that's number 2, and so it didn't. I don't think it incremented right. All right. That just means we've got stuff to fix. Let's do the first one. So I'm just going to focus on the first one. I am going to comment out. And string of 0 bytes. Let's go to the execute. Okay. For the execute, sorry, that is in the 14. Okay. You think I've had these memorized, but nah. So my size is the bytecode plus 1. That's fine. And my total bytes is the ceiling of that. Now, I need to make sure that my stack has that many bytes in it. Whoops. And so I need it to be bytes, which in this case is going to be 0, so that's fine. And now I need to construct the string. And so I'm going to have a string called temp. Sure, why not? Do it like that. Be consistent, Corey. And now yes, I can do this. For int I is equal to 0, I is less than bytes plus plus I. So we're going to go through each byte, and now for int j is equal to 0, j is less than size of uint 64t, plus plus I. All right, there's some other stuff I could do. If, now what I need is I need to make sure that I'm not going past size. So if I times, so I times 8 plus j, if that is less than size, then it's safe to do what I'm about to do. And that is, I'm going to take The problem is the bytes on the stack. Oh, no, wait, they're not on the stack. They're on the program. I'm not... Oh, wait, I am executing. So they're in... They're in order. No, I'm putting onto the stack. Sorry, I'm putting them onto the stack. So it's not that I'm doing a stack check. It's that I'm doing another execute program check, which is going to be 1 plus bytes. The 1 was for the size, and now the bytes for the rest of them. Okay, now I can get at this bytecode of PC plus 1 plus, and then I. That's fine. 1 plus I. So the first time it will be, that's even wrong. That should be 2. So PC of 2 plus I. Why? Because when I is 0, that means it's the 0th byte, the first byte, and it needs to be whatever the current program counter is, plus skip over the size, and then the next, and get to the next byte, plus 0. Okay, that's right. Now I need to get the however many bytes of each one. So the J is going to be byte 0, byte 1, byte 2, byte 3. And I'm trying to think, what's the best way of doing this? If there's probably a faster way, but if I shift it left by, the question is how many bytes, it's going to be 8 times something. Well, when I'm on 0, it needs to be, I need the first one, so I need to 8 times 7. Or when I'm on the second one, it needs to be 8 times 6. So when I'm on the 0th, it needs to be a 7. So we'll say 7 minus J. Okay. Now all of that is going to be anded, for lack of a better word, with I think it's actually 0xFF. So that's 8. Yeah. Okay, so now can I do this? Can I do string plus equals and tell it it is an unsigned char? And then after I do all of that, whatever's left of string, not string, temp, push that on. It's probably not going to like some stuff. Let's see. J. Size T. You know what? I could even do the same here. For consistency, even though it's not required there. And Of course, it's not string, it's temp. What? No, I think that looks right. The question is now if I remove this, will the second one work? Will I get a high out of that? Okay, so the stack is empty. And so let's do this. Let me to do that. I'm going to look at the dump statement. So I'm not actually dumping the contents of the string, but I kind of want to. So can I just yank this? And say bytes size string Okay, so for either it's because it's not there, or, oh, and I'm not doing the dump program check here either after I know the bytes, and it should be plus bytes. One plus bytes. Yep, I did it in both places. So that's passing. And I think we've got a way of doing this. So the only reason I'm doing that is so that it clears out the no, it doesn't matter. It doesn't matter. And I'm just going to see out a capital X. Not see out. Just out. A capital X. Why? Because I want to see two capital X's. And I'm not seeing any. So that means we're not getting here. So out size and bytes. Yes, the best way of debugging. Print statements. Okay, look. The first one is saying bytes 0, 0. The second one is saying the size is 0, the bytes is 2. No. I'm wrong. It's already printed. The 0 is the 2 here. This is the size of 0, the bytes 2. I think that's right. How do we double check? Simple enough. Print debugging. Size 0, bytes 2. Size 2, but bytes is still 0. So, if I, instead of making this a high, if I make this a hello world exclamation point, I'm expecting that to have an infinite loop. All right, so just in the dump bytecode. Let's go back to this, shall we? I don't even think I want to exit. Let's go back and turn off the X. All right. Question is my infinite loop happening in the execute or in the couts? It's happening in the cout, in the dump bytecode. Okay, I needed to know that. So, what's happening? I is less than... I'm not executing anything. What I'm wondering... Oh! There. Yeah, that'll do an infinite loop for you. All right, so my bytes calculation is off. It needs to be 1 greater. But why? So my bytes is the ceiling of the size. Why? Because size is an unsigned int. There we go. The size is 0, the bytes is 0. The size is 12, the bytes is 2. Sure. Okay, so the only change is, first of all, my double loop. I needed that to be J, and I needed the double to be size. And I don't want to write that yet. I'm going to, why? Because it's going to automatically do this. So this needs to be a double. And then this needs to be J. Oh, I could have written it because that one needs to be commented out. Well, so it's not like it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Not 12. And what did we pass in? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It should be 12 nulls. And it's not. So this is the dump bytecode. I is less than bytes. That's fine. J. Oh, okay, because I'm in the out, I can say this. I can say, sorry, out is bytecode. First of all, this is just plus I. There we go. That's just to make sure that there's something there. If it's 0, 0, then we know that there's a problem. All right. That should be fine. There should be something there, right? Okay. And do I have IO manip in there? I guess it's compiling, so we're okay. Only 7F. And what is 7F? Pulling up ASCIItable.com. Hex. 7F is 177. Oh, I should have known that anyway. So, something's not right in our compile. So let's go to the compile. Where is that going to be? That's AST node string. Of course. Look at this. Look at what I did. Mod by that is equal to -1. Still getting 7F. Okay. But still, that was wrong. So temp is going to be OR of this val sub I. This will be ugly, but who cares? Look at that. I get a 72, which, according to this here, 72 is capital H, 109. As an M. Okay, so something's not right. Something is not correct here. Val.length. Oh, because I'm doing an OR equal. I figured it out. Well, I mean, I see the problem. Do you notice what I'm not doing? So I've got this temp, and I'm OR equaling it with this val. But before I did that, I should have said temp shifted left by 8. Or rather, size of uint 64T. Oh. Forgot my equal sign. Hey. This is looking so much better. Okay, I would expect the numbers to be growing. That's fine. So I can take out that. And where else am I outing? That's going to be in the bytecode, or excuse me, in the running. So yeah, where's bytecode? All right, and hey, look, 0 string hello world, and it loaded hello world, and I had told it hi. So go back to my tests, and this should be hello world exclamation point. Okay, so you say those look the same. Why aren't they comparing? And I think I know why. I think it's because in my garbage collector, well, if I were to say here, string hello world, I think it's going to pass. It does. So I don't want to say string hello world because I'm lazy, which means I need to go to my garbage collected.hpp and I think I need a const there. And now it's going to complain because it can't find it. That's it. B10. And now this to-do will work. Yep. Now I just need to, I can remove the dump bytecode here. And so an empty string works and a string works. Oh boy! Say, Corey, that took a while to get there. Yeah, it did. But you know what we've got now? We've got strings. And so, let's just try something, shall we? Our add, right here. Let's, 10. And this one can be a 10. And we're going to say, what do we say? We can do the hello plus a space plus, where's the plus? There we go. World, exclamation point. And we should get out hello world. And if we cout p10.dump bytecode, we should see 3 pushing a string, hello, space, and we add them together, and then a string add world. Yes. Other things should just work. So subtract, we don't do multiplication, we're not doing division, we're not modulo, unary, minus, parentheses, we don't need to do it. We could work on typecasting int as a string, but or float as a string, but we'll worry about that later. Less than. Let's do one. This is going to be 16, and this one is going to be A is less than did that wrong, is less than B. That should be true. Before we go any further, let's test that. It passes. Okay. And B is less than A should be false. Everything still passes. I'm not going to continue, I don't think, because I think that the less than or equal is fine. Greater than or equal to. We'll probably test the equality, right? Because the others rely on less than and equality. So, so this will be 20. Let's just get it set up. A is equal to B, and the answer should be true, but we're gonna, there we go. So this should be 23 and 24, 4 and 23. Okay, so this should be, nope, false. This should be true. Uh, 24. Oh. That should be an A. When you write the wrong answers, there you go. Okay. The not equal, well, the statement should be fine. An identifier, can we assign a string? I don't think we really need to test that as much. Do while. I mean, I think we're good. So, what I normally do over here is make clear, make clean, make test. While it's doing that, let's do our sanity check of get status. Okay. Get diff. This all looks correct so far. All right, now you may be wondering why we added this thing. I'm looking for it. String error, right? And somewhere, where's the, I'm looking for where I added it to. Oh, there it is, string error. So here's where I added it to Bison. And we don't do anything with it. But the reason is because if we send string error, Bison will give us an error like expected something, found malformed string. It would have said like expected expression or this or that, found malformed string instead. That's why we include it. Okay, so everything looks good. We're going to add our include AST node string, include computed expression string, our source AST node string, our source computed expression string, add strings to language. Sure. Just do it. It's two commits. I'm sorry. All right, that's all there. rm-rf docs, make docs-pdf. WSL view docs, HTML index. Open on the other screen, but that's all right. Just pulling it here. And of course, now in our files, we've got this AST node string. And under classes, AST node string. Well, and plus the computed expression string. But yeah, it's there. Beautiful. What episode are we on? This is episode 29. For episode 29. There we go. And it is there. Last but not least, I always like to just check this out to see where we are. Okay. 3,900 lines with codes and comments. That works. Well, we did it. We have added strings to our language. We haven't met our goal. Our goal is to have Unicode strings and have native Unicode support. We do not have that yet. We just have support for strings. And it's going to take some work to get Unicode in. That's why I kind of broke this apart into a little bit. I may not tackle Unicode right away. The next one we may go for an easy win of adding for loops. Sometimes you just want to take the easy stuff, intersperse all the hard stuff with some easy stuff. And to be honest, I've been dreading this string part because I know how much work it is and how much is ahead of us. But once it works, it's beautiful. And having said that, I think we are at a good stopping place. And as always, thank you for joining us on the journey. I hope it's been fun. Have a great day, and I'll see you next time. Bye.